A video codec is software or a device that provides encoding and decoding for digital video, and which may or may not include the use of video compression and/or decompression. The compression may employ lossy data compression, so that quality measurement issues become important. Shortly after the compact disc became widely available as a digital format replacement for analog audio, it became feasible to also store and use video in digital form. A variety of technologies soon emerged to do so. The primary goal for most methods of compressing video is to produce video that most closely approximates the fidelity of the original source, while simultaneously delivering the smallest file size possible. However, there are also several other factors that can be used as a basis for comparison. Introduction to comparison: the following characteristics are compared in video codecs comparisons. Video quality per bit rate. Commonly, video quality is considered the main characteristic of codec comparisons. Video quality comparisons can be subjective or objective. Performance characteristics such as compression, decompression speed, supported profiles options, supported resolutions, supported rate control strategies, etc. General software characteristics are for example, manufacturer, supported OS, version number, date of release, type of license, supported interfaces, price. Video quality: the quality the codec can achieve is heavily based on the compression format the codec uses. A codec is not a format, and there may be multiple codecs that implement the same compression specification. For example, MPEG-1 codecs typically do not achieve quality size ratio comparable to codecs that implement the more modern H.264 specification. But quality size ratio of output produced by different implementations of the same specification can also vary. Prior to comparing codec video quality, it is important to understand that every codec can give a varying degree of quality for a given set of frames within a video sequence. Numerous factors play a role in this variability. First, all codecs have a bit rate control mechanism that is responsible for determining the bit rate and quality on a per-frame basis. A difference between variable bit rate and constant bit rate creates a trade-off between a consistent quality over all frames, on the one hand, and a more constant bit rate, which is required for some applications, on the other. Second, some codecs differentiate between different types of frames, such as key frames and non-key frames, differing in their importance to overall visual quality and the extent to which they can be compressed. Third, quality depends on pre-filtrations, which are included on all present-day codecs. Other factors may also come into play. For a sufficiently long clip, it is possible to select sequences that have suffered little from the compression, and sequences that have suffered heavily, especially if CBR has been used, whereby the quality between frames can vary highly due to different amounts of compression needed to achieve a constant bit rate. So, in a given long clip, such as a full-length movie, any two codecs may perform quite differently on a particular sequence from the clip, while the codecs may be approximately equal in quality over a wider sequence of frames. Press releases and amateur forums sometimes select sequences known to favor a particular codec or style of rate control in reviews. Objective video quality. Objective video evaluation techniques are mathematical models that approximate results of subjective quality assessment, but are based on criteria and metrics that can be measured objectively and automatically evaluated by a computer program. Objective methods are classified based on the availability of the original video signal, which is considered to be of high quality. Therefore, they can be classified as full reference methods, where the whole original video signal is available, reduced reference methods, where only partial information of the original video is available, and no reference methods, where the original video is not available at all. The main FR metrics are peak signal-to-noise ratio, the most widely used video quality metric during the last 20 years. However, the validity of this metric is limited. It is conclusive only when the same codec and content is being compared. Structural similarity, a new metric that shows better results than PSNR at the cost of a reasonable increase in computational complexity. VQUAD HD and ITU-T J341 standard. The new standard was recently approved by ITU-T as J341. The new VQUAD HD ascent algorithm was developed by Swisscall in 2008 Euro 2010. It was the best performing model in the HD TV competition to find the new standard that was organized by the Independent and Non-Commercial Video Quality Expert Group. More information on VQUAD HD can be found in the technical white paper Video Quality Measurement for High-Definition Video Signals, available for download from white paper. Some other metrics have been suggested by Video Quality Experts Group, private companies, and universities, but are not widespread. The main comparison method is the so-called RD curve, in which a metric value is plotted against the y-axis and the bit rate against the x-axis. Some example NO metrics are: blocking measure a measurement power of so-called blocking artifacts, blurring measure a measurement of common video blurring, subjective video quality. This is concerned with how video is perceived by a viewer, and designates his or her opinion on a particular video sequence. Subjective video quality tests are quite expensive with regard to time and human resources. There is an enormous number of ways of showing video sequences to experts and of recording their opinions. A few of them have been standardized. They are thoroughly described in ITUR Recommendation BT 500. The following subjective video quality comparison methods are used. Double stimulus impairment scale Euro suggested in ITUR BT 500-11. Double stimulus continuous quality scale type I and type 2 Euro suggested in ITUR BT 500-11, stimulus comparison adjectival categorical judgment Euro suggested in ITUR BT 500-11, subjective assessment method for video quality evaluation, MSU continuous quality evaluation. The reason for measuring subjective video quality is the same as for measuring the mean opinion score for audio. Opinions of experts can be averaged, and the average mark is usually given with confidence interval. Additional procedures can be used for averaging. For example, experts who give unstable results may be rejected. In case of video codecs, this is a very common situation. When codecs with similar objective results show results with different subjective results, the main reasons can be, pre- and post-filters are widely used in codecs. Codecs often use pre-filters such as video denoising, deflicking, shacking, etc. Denoising and deflicking normally maintain PSNR value while increasing visual quality. Shacking greatly decreases PSNR, but increases visual quality. Post-filters show similar characteristics. De-blocking and de-ringing maintain PSNR, but increase quality. Graining essentially increases video quality, especially on big plasma screens, but decreases PSNR. Note: all filters increase compression-decompression time, so they enhance visual quality but decrease the speed of coding and decoding. Motion estimation search strategy can also cause different visual quality for the same PSNR. So-called true motion search commonly will not reach minimum sum of absolute differences values in codec ME, but may result in better visual quality. Such methods also require more compression time. Rate control strategy. VBR commonly cause better visual quality marks than CBR for the same average PSNR values for sequences. It is difficult to use long sequences for subjective testing. Commonly, 3 or 4 10-second sequences are used, while full movies are used for objective metrics. Sequence selection is important. Those sequences that are similar to the ones used by developers to tune their codecs are more competitive. Performance comparison, speed comparison. Number of frames per second commonly used for compression-decompression speed measurement. The following issues should be considered when estimating probable codec performance differences. Decompression frame time uniformity. Big differences in this value can cause annoyingly jerky playback. SIMD support by processor and codec. For example, MMX, SSE, SSE2, each of which changed CPU performance on some kinds of tasks. Multi-threading support by processor and codec sometimes turning on hyper-threading support causes codec speed to decrease, RAM speed generally important for most codec implementations, processor cache size low values sometimes cause serious speed degradation, for example for CPUs with low cache such as several of the Intel Celeron series. GPU usage by codec some codecs can drastically increase their performance by taking advantage of GPU resources. So, for example, codec A may, on modern computers, give slower performance than codec B. Meanwhile, the same pair of codecs may give opposite results if running on an older computer with reduced memory resources. Profile support. Modern standards define a wide range of features and require very substantial software or hardware efforts and resources for their implementation. Only selected profiles of a standard are typically supported in any particular product. The H264 standard includes the following 7 sets of capabilities, which are referred to as profiles, targeting specific classes of applications. Baseline profile, primarily for lower-cost applications with limited computing resources. This profile is used widely in video conferencing and mobile applications. Main profile, originally intended as the mainstream consumer profile for broadcast and storage applications, the importance of this profile faded when the high profile was developed for those applications. Extended profile, intended as the streaming video profile, this profile has relatively high compression capability and some extra tricks for robustness to data losses and service stream switching. High profile, the primary profile for broadcast and disk storage applications, particularly for high-definition television applications. High-10 profile, going beyond today's mainstream consumer product capabilities, this profile builds on top of the high profile, adding support for up to 10 bits per sample of decoded picture precision. High 422 profile, primarily targeting professional applications that use interlaced video. This profile builds on top of the high 10 profile, adding support for the 422 chroma sampling format while using up to 10 bits per sample of decoded picture precision. High 444 predictive profile, this profile builds on top of the high 422 profile, supporting up to 444 chroma sampling, up to 14 bits per sample, and additionally supporting efficient lossless region coding and the coding of each picture as 3 separate color planes. Multival high profile, this profile supports 2 or more views using both interpicture and MVC interview prediction, but does not support field pictures and microblock adaptive frame field coding. The standard also contains 4 additional all-intra profiles, which are defined as simple subsets of other corresponding profiles. These are mostly for professional applications. High 10 intra profile, the high 10 profile constrained to all intra use. High 422 intra profile, the high 422 profile constrained to all intra use. High 444 intra profile, the high 444 profile constrained to all intra use. CAVLC 444 intra profile, the high 444 profile constrained to all intra use into CAVLC entropy coding. Moreover, the standard now also contains 3 scalable video coding profiles. Scalable baseline profile, a scalable extension of the baseline profile. Scalable high profile, a scalable extension of the high profile. Scalable high intra profile, the scalable high profile constrained to all intra use. An accurate comparison of codecs must take the profile variations within each codec into account. See also MPEG2 profiles and levels. Supported rate control strategies. Video codecs rate control strategies can be classified as variable bit rate and constant bit rate. Variable bit rate is a strategy to maximize the visual video quality and minimize the bit rate. On fast motion scenes, a variable bit rate uses more bits than it does on slow motion scenes of similar duration, yet achieves a consistent visual quality. For real-time and non-buffered video streaming when the available bandwidth is fixed for example in video conferencing delivered on channels of fixed bandwidth a constant bit rate must be used. CBR is commonly used for video conferences, satellite and cable broadcasting. VBR is commonly used for video CD-DVD creation and video in programs. Software characteristics, codecs list. The Kshift.org Foundation has negotiated an irrevocable free license to Theora and other VP3-derived codecs for everyone, for any purpose. DivX Plus is also known as DivX 8. The latest stable version for Mac is DivX 7 for Mac. Native operating system support. Note that operating system support does not mean whether video encoded with a codec can be played back on the particular operating system. For example, video encoded with the DivX codec is playable on Unix-like systems using free MPEG-4 ASP decoders, but the DivX codec is only available for Windows and Mac OS X. Technical details. Theora streams with different frame rates can be chained in the same file, but each stream has a fixed frame rate. Freely available codecs comparisons, list of freely available comparisons and their content description, see also. Comparison of media players, list of video players, list of codecs, open source codecs and containers. Comparison of audio coding formats, comparison of container formats, comparison of video encoders, comparison of video editing software, notes and references. External links, MSU Subjective Comparison of Modern Video Codecs, ITS, Video Quality Research, Evaluation of Subjective Video Quality of Mobile Devices.